Related to the overlap integral and coupling into waveguide, we take a look of one example. Here we have an incident wave which is described by a Gaussian function, and we have also a waveguide whose waveguide mode is presented by a Gaussian function. The width of the mode is described by W for the incident and W2 for the waveguide mode. The nominator of the overlap integral has the product of the incident and the waveguide mode. Then we take an integral and finally absolute value of the integral. In the denominator we have the integral of the intensity of the incident field and multiplied by an integral of the intensity of the mode in a waveguide. When we insert the functions, we end up to an expression like this. And in this expression we have now integrals of the Gaussian functions, which in general are a bit nasty to calculate, but fortunately this is already calculated for us, and we can use the general formula for integrals of the Gaussian functions, and after this exercise is just bookkeeping to keep track of the different coefficients. So if we work our way for the integration of the nominator in a couple of steps, we end up in a kind of a simple expression which includes the width of both of the modes, both the incident and the waveguide mode. The same applies for the denominator. So if we calculate the integral, use the equation here, we end up with two expressions for the incident field and for the waveguide mode. And let's now insert this into the overlap integral and calculate the coupling efficiency between these modes. Now, if we insert the nominator and values in denominator, we end up with the expression like this for the power coupling efficiency between the incident Gaussian field and the waveguide mode. And in general, this is always smaller than 1, except when the widths of these modes are the same. And this takes place exactly when the two modes are exactly similar. And if they are even slightly dissimilar, the coupling efficiency will always be smaller than 1.